Okay, we're going to talk today about moving on to a wave model of light from the particle model of light. We've been talking about the particle model for a few weeks, and it turns out that light can behave as a wave as well. So if you look at this illustration, this is from your textbook. The first picture up in the upper left here, it looks like a light bulb striking the light striking a screen, and there's a little obstacle in front of it, and you see how if the light acted like particles, you'd see that little shadow there. And if you think about what's happening when the light particle comes in, it strikes a surface. We assume it's a perfectly elastic collision. It bounces off in the opposite direction. And if it's perfectly elastic, the velocity coming off is the same as the velocity going in. And so there's no change in the component of the velocity vertically, but the horizontal component reverses direction. But you can see that vertical speed stays the same. That would be the particle model. Well, what actually happens, if you remember, when light goes into a denser medium, so this is from our refraction unit, when light comes in from a less dense medium into a more dense medium, it actually bends towards a normal. Okay, so here's a normal line right here. What that suggests, if it bends towards a normal, is that vertical component of velocity is actually getting greater. And that doesn't make sense because this is supposed to be the more optically dense medium. And if that's a more optically dense medium, then the light shouldn't speed up like it's doing here. It should slow down. It should bend away from the medium when it goes into a more optically dense substance, like from air into water or air into glass. So that doesn't make sense. That's the first issue with the difficulties of the particle model of light. Maybe a more obvious one, if you think about it, is if you took a flashlight. So here's my flashlight right here, and I'm shining light through a piece of cardboard with two slits cut in it. What you would expect to see are two areas of light on a screen like this. So you'd expect to see just two rectangular shapes of light and then shadow everywhere else. But here's what actually happens. So if I have light rays coming in, and this would be like a laser, okay? So a monochromatic, meaning a single colored laser, like a red laser. It comes into these two slits. Each one of the slits acts as a source of light. So what you end up seeing on the screen is over here on the right, you end up seeing these bands of light and dark. And it's not at all what you would expect to see. There's nothing in the particle model of light that would explain these little tiny bands of dark and the very bright bands. So something else is going on here. And you can see in this illustration, this looks like maybe waves, like we had a ripple tank demonstration last year in AP Physics 1. If you're in my class, you might remember that. I'm going to talk about that a little bit later. But light, if it behaved as a wave, could explain what we see over here. And this is a very famous experiment. This is called Young's double slit experiment. And we're going to talk a lot about that in this unit. That's a major part of this unit, is the Young's double slit experiment. But what could explain this a little bit also is how does a wave create those patterns of bright and dark areas? So we talked about this really briefly in AP Physics 1, which was Huygens' principle. Huygens was a Dutch guy back in the 1800s, and he had a concept of, if you think of water waves coming into the ocean, so this is like a long wave, horizontal, it's parallel to the shore, it's coming in, it's just a straight line. He envisioned that each single point on that wave, okay, and that doesn't mean the point has a specific size, it's just any individual location on that wave was its own source of a disturbance. So for instance, you've got this semicircular disturbance here that's centered right here. You've got another semicircular disturbance right here that's centered right here. So each one of those is a different source of a wave almost. So if each one of those is a different source of a wave, then you can see as this wave approaches, over on the right, I'm in the right-hand picture now, as this wave approaches a new medium, then if it slowed down, if this was the more optically dense, then the space between the wave fronts would be a little bit less because it's not moving quite as fast. So it's slowing down the wave as it gets into the more optically dense medium. That's consistent with what we know happens with a more optically dense medium. The speed of light goes down. Well, this is showing something coming in straight along a normal line when the medium is more optically dense. What happens when it comes in at an angle? So when it comes in at an angle, so you can kind of see here, if I can zoom in a little bit, what you can see here is as it comes in at an angle, so once these points on this side of the wavefront, those are all sources of their own disturbances, remember, when they get into the medium first, because they're coming in on an angle, so these guys are going to hit this border first, they slow down. So the wavefront kind of bends to the left, if you would, or towards the normal. Actually, it's bending this way. Okay, these guys are still in their faster medium out here, so they're still moving pretty fast, so they're like this. So you get this effect of bending towards a normal with each one of those wavefronts kind of twisting a little bit as it slows down in the second medium. That's consistent with what we see. Let's back out here again and look over here. And it's just the opposite. I don't need to go through this in any kind of detail, but I think it's just the opposite over here. When you're going into a faster medium, these guys, this side gets into the faster medium first when it crosses over right here. So it's going to speed up. So it's going to bend away from the medium, or normal right there. These guys are still in the slower medium over here. They haven't passed across the border yet, so they're still moving slow. So that would make sense that the wave fronts bend away from the normal once they get through the boundary between the two media. So that's an explanation of if light really was a wave, it would explain that behavior of bending away and towards the medium or the normal line when it passes into a new medium. Okay, so I've got a video here I'm going to show you that kind of demonstrates some wave behavior, and it's going to help us to understand if what we just hypothesized with the bending of light as it goes into a new medium, if waves would actually behave that way, and if wave behavior would explain that double slit bright dark band phenomena. So I would normally do this in class. We have ripple tanks in the lab, and we did them in AP Physics 1 if you remember last year. But unfortunately, distance learning, I can't do that. But I found a nice video of a guy, a British professor, who seems pretty good. And so I'm going to play this. I'll stop it once or twice, okay?
This device is known as a ripple tank. We can show it to show a wide variety of wave phenomena, but the particular one I want to show here is interference between two sources. The ripple tank consists of a tank, shallow tank of water, a light here which projects through the water, and so you can actually see the ripples on the surface below. And here we have a vibrator with two arms. At the moment I've got one of them out of the water. When I turn this on, you'll see it produces circular waves. They simply spread out from that point there, more or less constant speed. There's a little bit of dispersion.
So notice that these are the wave fronts. Okay, the bright, the bright edges, that's kind of the back of it right there. Let me get rid of that. The front edge of that bright line right there, those are wave fronts, okay? So those are crests of waves, and then these are troughs of waves right here. These are the bottom of the wave, are the dark edges.
But very little, and so you see the waves spread out in a circular fashion. That's not particularly interesting. It gets more interesting when we put the second source in. And now we have the two sources in phase producing ripples, one there and one there. And you can see fairly clearly what happens in this case. There are places where the waves add up, i.e. you get constructive interference. For example, along the line perpendicular to the line joining the two, you'll get constructive interference and you'll always get a maximum. A little off to one side, you'll see that you get destructive interference. The waves are out of phase there, they cancel out. And similarly over here, they cancel out. So there is destructive interference, there is destructive interference, there is destructive interference, there is destructive interference. In between, you have a maximum of constructive interference. This is a fundamental principle of the Young-Slits experiment that we do with light. However, there's an extra twist when you're doing the experiment with light that doesn't arise when you're doing it with water waves. We can change the frequency, which in turn means changing the wavelength. You see, the pattern qualitatively doesn't change, but as we increase the frequency, the interference lines get closer together. We can't go too high because we burn the motor out.
Okay, so that was a good demonstration of wave interference. So that was when two crests of waves touch each other and add up, or a crest and a trough add up to each other or meet each other and cancel out. So that's called wave superposition, which you might remember from AP Physics 1, where you've got two waves occupying the same space at the same time. We're going to talk a lot more about that, but it seems like the wave behavior would explain what that Young's double slit experiment, the results of that, which were the bright and dark bands. So a couple things I want to remind you of about the behavior of waves in general, not just light waves, but any waves. The speed of light in a given medium is related to the index of refraction for that medium. This is something that we talked about again in the last unit, which was on refraction, where numbers are always, the index of refraction, this variable n, is always larger than 1, because light can never go faster than in a vacuum. So 3 times 10 to the 8th meters per second is the speed of light in a vacuum. The speed of light in this second medium is always going to be less than that. So the larger the value of n, let's say diamond at 2.2 or 2.4, the speed of light in that medium is much, much less than it is in a vacuum. What determines the speed of a wave, if you remember from AP Physics 1, it's always the medium. The medium is what determines the speed of light in that particular medium. So if it's with light, if it's more optically dense, it's going to move slower. If it's less optically dense, it'll move faster. The next slide, I'm going to talk a little bit about the wave equation, which can be a little bit confusing, as simple as it seems. So the wave equation is just v equals f times lambda. V is the speed of the wave. F is the frequency of the wave. It's that F that looks like the force of friction. And then lambda is the wavelength measured in meters. Remember, frequency is in hertz. That's cycles per second. A cycle is not really a unit. It's just a count of a number. So when you multiply it times meter, the cycle goes away. And these units on the right side end up being meters per second, which is consistent with what you would expect on the left side for velocity, would also be meters per second. The reason I said in the last slide that was up that this can be a little bit confusing is you might think that frequency and wavelength determine the speed of the wave. They don't. They don't determine the speed of the wave. This is determined by the medium. So the fact that those waves were just traveling through water, when that professor changed the frequency of the wave, what ended up changing was the wavelength, and the speed of the wave remained constant. Really hard to see in that video because of the refresh rates of the video. It almost looked like the wavefronts weren't moving sometimes because of that refresh rate. But in fact, as the frequency increased, the wavelength became smaller. So as this went up, this came down by the same factor, so that this speed remained constant. So this is not a cause and effect equation. You can calculate the speed of the wave if you know these other two things, but those other two things on the right side, frequency and wavelength, won't determine the speed of the wave. That's all for today. It's a long screencast. I'm going to talk in the next screencast a little bit about some of the ways we can learn more about Young's double slit experiment.